Good evening, everyone. This is Celso Batalha, Physics 2B, and I apologize for not being in class this evening, and I would like to highlight points of chapter 20 that need to be highlighted, so you can go through your homework and have a wonderful spring break. So we needed to go over motional EMF, some basic idea related to generators, inductors, and RL circuits, which is a circuit that has one component which is new, called inductor, and another one resistor. Remember RC circuit? Okay, it's kind of the same thing. But I mean, the core material in this chapter is, yes, induction. Remember, induction is that phenomena by which, if there are changes in the magnetic flux, the amount of field lines crossing a loop, you gotta have a loop, you might ended up with some currents. And we went through several examples in class, and but I'm sorry, I just need to pull up this palette. But we went through several examples in class on how induction works and how important it is for what we do. And here's one example, for instance. I'm pretty sure you have been driven in a highway, and then your car goes over. So here's a beautiful car, right? And here's you all happy, driving your car. Car is going that way with a certain velocity, and somewhere in here you have these big power lines, right? And I'm not drawing in perspective. In fact, I'm a terrible drawer. But anyway, so you're going in this direction. Here's the right highway, right? And you have these power lines above you. You have to go under them. And just to make it simple, let's say these power lines are cables that carry not milliamps like in our lab, but a heck of amps. And so, which means, if just for sake of example, if the current is going towards the whiteboard, then as we have been learning, the magnetic field kind of a loop around like this, right? The magnetic field these cables generate is something like this. It goes clockwise because you put your thumb in the direction of this whiteboard, and then you circulate like this, right? And there you go. So which means, right here, so if you think, you have on the highway, you have circulating, that's so terrible, circulating magnetic field lines, and of course they become weaker as you go away from the power lines. But I mean, we don't see it, but the point is the car is going to go and into these walls or these clouds of magnetic field lines, all of them. So as they circulate this way, right? And the intensity of the field increases as you approach the power line. I mean, when your car is here, that's your car. When the car is here, the intensity of field lines is much more than it is right here, right? So you almost have nothing. But here's my example. Let's say, just for the sake of example, you have a crappy radio, and your crappy radio in AM frequency has a circuitry that one of the components is a loop, something like this, and I'm expanding, right? Now imagine for a while, as your car moves, your radio and the loop inside also move that way. So you know what's going to happen? Can you guess what's going to happen? So this little circuit component will have magnetic field lines poking through the loop. Now, according to Lenz's law we learned in class, so as the car approaches this region, the amount of field lines crossing the loop going up increases because the intensity of the field is getting stronger as you go that way. Which means, according to Lenz's law, let me get a red marker. There you go. According to Lenz's law, Mother Nature creates a induced field that opposes that growth. Remember that? You guys did a lot of exercise in class. And because of this growth in induced magnetic field, which current in the loop creates that? Well, has to be a no, wait a second. Has to be a current that circulates the loops like this. How do we figure that? That's the current induced. So how do we figure that? Well, you place your thumb on top of the wire right here. Use your thumb. No, I should make a thumb kind of a bluish. Not because you're cold or anything, it's because just to differentiate the color. This is the thumb, right? And the rest, I'm not gonna draw the rest of the hands. It's gonna be indecent, I think. I'm a terrible drawer. So the thumb is like this, and then you take your 4 fingers of your right hand, and then you curl them to grab the wire. And when you do that, the fingers will go this way, and that points the direction of the induced field, and that should be the right thing. So you have the induced field to begin with because it counterbalance the growing field lines inside the loop because of this external field here, external cable lines. Now, what these currents will do, oh, God knows what. I mean, this current, this circuit might be connected with some other circuit that might draw some changes in your radio speakers, and then you might hear, you know what, noise. So what is the source of noise when you go under a power line? Well, is that, I mean, you have unwanted current generated in your radio. So modern radios create shields that prevent these kind of things happening. Okay, again, induction is the good thing. So let's go to the book and see what is you have to do it. In fact, let me write down what are the basic things we need to know. The first is this slide wire generator, or electric motive force, that's generated when a bar of conductive material move inside a magnetic field. So we have this basic equation here that I will show you how that happened. So this is the first one. The second one, we are going to define something called inductor. An inductor will pull another term called self-inductance. Symbol of it, L, and the unity of it, Henry, H. Okay. The other thing that I will finish up is in a circuit that has a power supply, you have a resistor in there, and if you have to have an inductor, by the way, the circuit symbol of inductor is it's like a solenoid, and you know why. I'll show you. So you have an inductor like that. What the inductor will do is to retard the growing or the diminishing factor in currents on your circuit. So let's say you have a current in your circuit, and you have a switch here. Let me bring a switch. So you have a switch in your circuit, And of course, when the switch is open, the circuit is open, you don't have current, right? Current is 0 amps. But once you close your circuit, let's say you close now, so your current for a brief period of time goes from 0 amps to some final value that I don't know. It's called I. So there is a change in the current in the circuit. Now remember, your circuit here is a loop, right? And it has a current that is growing in it. And in addition, you have something called inductor in it. So what the inductor is going to do is to retard the growing current from this initial value to this final value. And we are going to see a current dependence that is equal to epsilon over R that multiply 1 minus so that at time equals 0, so when you place time equals 0, what is the current in your circuit? Is 0. Remember, in capacitor was different. If you had a capacitor here, at the time equals 0, the current was I naught, was the maximum current, and as the capacitor would be charging, then the current would grow to would diminish and waning down to a final 0 value. With inductors, it's different. So you have a different situation going on, and that is, once you close your circuit, your current grows from an initial 0 value to some final value, and this is the equation describing that change. By the same token, the current and the voltage on your inductor will make changes accordingly. So I'm not gonna be so crazy, although I will do problems in the classroom the week after spring break, but we are going to do several of these exercises in the lab. So I have the equipment, and then you're going to see these circuits, this operation going on, and the whole AC subject, which is the next chapter in our book, alternating current. So all of these will be now explored in lab, basically. Okay, so I'm not for instance, this chapter, I'm not gonna lecture on it. It's gonna be totally practical, so that we can pretty much go on the subject you're supposed to be exposed to. Okay. Emotional electric motive force. Take for now, or imagine now, there is a bar. By the way, let me time myself. I will be another 30 minutes in here. So there is a bar that is moving to the right with a velocity v, and there is a magnetic field going into the white page. So we learn, if this bar is made of conducting material, and you have free ions in it, and just for the sake of thought, let's consider these free ions to be positive. Okay? You know, this is not true. What in reality moves in the conductor in most of the cases are electrons. But just to make it our train of thought functioning properly, let's make positive. So we are dealing essentially with induced with the conventional current rather than electronic real currents. Okay. So then you have your bar that is moving the electric field, and we learned that F is equal QVB. Remember that? The magnetic force is equal to QV cross with B. And we use our right-hand rule to decide what is the direction. So the right-hand rule, you have a thumb like this, and then you place your 4 fingers. 1, 2, 3, and 4 fingers. Yeah, there you go. So this is 4 fingers. This is your thumb. Kind of a skinny thumb here. That's your thumb. Looks like a. That's not good, huh? But anyway, that's suppose this is your right hand, and then you put your 4 fingers in the direction of the velocity vector, right? And in that example we have in the book, we have a magnetic field that goes into the board, and you have a velocity vector going that way. So these 4 fingers are placed in the direction of the velocity vector, and then you curl your fingers to grab the field using the least angle. So when you do that, you're going to switch this V vector towards the field that goes into the board, and your thumb is showing the direction of the magnetic force. So the magnetic force is showing up, which means the magnetic force in positive charge in this example are, hey, what's going down? Wait a second. No, because it's putting negative charge in motion. Oh yeah, because it's a negative charge. Look at that, negative charge. But anyway, so in my example here, I was considering your charge being positive. Remember conventional current? The final product, it doesn't matter, as I show it to you here. Here. So imagine positive charge, bar moves this side, you bend your 4 fingers towards the field that goes into the board. This top part of the bar will be accumulated by positive charge, and consequently the negative charge will accumulate down here. Can you see that as this bar moves? Now think about an airplane. So in reality, airplanes, so the Airbus just fell on. What a sad news. I mean, I like computers. We use them, but computers are crazy. Sometimes they stop working. They don't let us know. Like my dishwasher. Suddenly the dishwasher work, does all the cycle, and when it's 1 minute to finish, it doesn't want to stop working. It keeps working, right? So 1 minute in all these possible settings, it gets to 1 minute and keep working, and then somehow it was stopping for a month, and no one paid attention to that, and the dishwasher just working hours, to complete the cycle. And last month my bill went crazy, and I said, what's going on here? I mean, I'm out of the home quite a while, so I found the problem. Now needs to be fixed. But anyway, so computers, when they fix, sometimes it's hard to find what the problem is. But so an airplane moves through a magnetic field lines, and these kind of things really happen. You have an accumulation depending on the orientation of the airplane with respect to the field. In other words, the direction of velocity vector with respect to the magnetic field. You're gonna have a voltage differential build up in the wings of your airplane. Remember the airplane? If the airplane is like this, so I have an airplane right there, right? And the windows are here, beautiful windows, and then you have the wings like that. Airplane moves like this, V. So the wings are made of metallic conductive material. So you ended up, if the field goes into my whiteboard, with a positive and negative concentration of charges. In other words, you have a del V, a change in voltage between those two ends. And we learned that del V is equal EL, the electric field. But which force is the one bringing the charge up there? It's the magnetic force, QVB. QVB. And what is electric field? Well, the electric field, in fact, del V, That's del V, the changing voltage. The changing voltage is the electric field times L, and sorry, something here is fishy. I'm sorry, this is not correct. I mean, this is correct. The voltage, the differential voltage is the electric field. So we have an electric field from positive to negative, as we did in the lab, times the length of this airplane wings gives the differential in voltage. But if there is an electric field, and if the charge gets to some stationary situation, they don't move anymore, the electric force QE, remember the field, is equal to QVB, right? So, and then we have the electric field equal to, nice way, the first time we are equating electric field with the magnetic field. So this electric field on the wings is being generated by this external magnetic field. In the case of an airplane, it's Earth magnetic field, and through the velocity of the airplane. Isn't that cool? It's really cool. So you can based on the fact you know E, you can multiply by L, and then you have the whatever voltage. I mean, the voltage is not big, it's small, but something that is happening. Okay. All right. So examples of this situation: a slide wire generator. This is a generator, a type of generator. So imagine you have a circuit with a resistor that is closed through this slide wire, right? And you have a mechanical device that moves this slide to the right. It could be a horse that is attached to by a cord through this slide wire and moves to the right. Okay. So as this slide wire moves to the right with an applied force, right? So it's an external force. So see the things that happen when this takes place. As the slide wire moves to the right, see the number of field lines inside the loop? What is happening with it? It's growing. So as the slide wire moves to the right, more field lines happen to be passing through the loop. According to Lenz's law, the magnetic flux is increasing. What's the circuitry? What's the loop? What Mother Nature does, according to Lenz's law? It creates a induced magnetic field that opposes that growth. And the induced magnetic field will be poking out of the paper towards you that is looking to this figure here. Okay. So if I go to my smoother, this is messy. Let me take this out. So again, so we have the magnetic field like this. We have a resistor right there, and you have some circuitry, and we put a slide wire here. So the slide wire is made of conductive material, and it can be slide over this circuit without resistance, just for now. And pretend there is something pulling, and I'm going to call this external force. It's pulling to the right. So what's going to happen? So as it goes to the right, you have a velocity associated with it. Positive or induced currents will start pulling up. Well, but now this is not an airplane, it's a circuit. So as it gets to this point, it keeps going this way. And the current keeps going this way. So if you have, instead of a resistor right here, if it's instead of a resistor, if you have Yeah, you know what they're going to do. If you have a light bulb, you're going to have power dissipated. And the current comes back and circulates. So we have a generator. So if you take a horse, or if you take water from a river, or if you have water from a river, you would need an infinite circuit here. But if you have a system that could bring this bar to the right, the current is going to go this way. Why? Because according to Lenz's law, as this circuit moves to the right, more field lines will be picked. According to Lenz's law, an induced field will oppose that growth. And by the way, what is the direction of the current? You place your thumb, your right thumb, in the direction of the induced current and curl your fingers to grab the field lines. So that is the direction of your induced current. So in reality, this is a slide wire generator. The electric motive force generated is equal to the magnetic field that is being generated times the velocity in which the bar moves times the length of the bar. Okay, that's it. Now this electric motive force, if you have a resistance given, and if you can measure that resistance, this is going to be equal to Ri. So you can quantify the current that way. So the current is basically this much. Applying Ohm's law, right? That's the current that goes through that. Good enough? Now remember, we are going to study AC. We are going to be studying AC. What if we have a system that allows this bar to go back and forth, back and forth, back and forth, back and forth? If you design a circuit like that, or an engine like that, or a generator like that, so then your current would go back and forth, back and forth, back and forth. The direction would be changing all the time. So we have a AC circuit or system. Okay. Take a look at the so-called self-inductance. And so in self-inductance, in fact, let me show you a picture of a generator and briefly explain you how a generator can come up with energy. So let's say you have a magnet like this one, north and south polarity, which means your magnetic field is going this way. Imagine you have a loop. Think about turbine, right? And think about you have a mega magnet, and there is a turbine that is allowed into rotation. And in fact, you have a turbine that is allowed to go into rotation, that is connected to the shaft, right? So as turbine rotates, because, well, the river is flowing, or because you have wind somewhere, or because you have coal that is being burned, and the steam used by the burning coal to warm up and boil the water, this steam generator is passed through some tube that rotates a turbine and rotates these things. The same thing with nuclear power. It's the same idea. You use radioactive materials to create steam, and the steam goes to pipe, and the pipe generates motion in turbines. Turbines are connected to these loops. These loops are somehow in the middle of magnets, and as they rotate, they generate what I will show you now. So so imagine this rotating clockwise in my design. So you have this bar over here, the top one, since it's going clockwise, has a velocity vector that way, correct? Now apply your right hand rule to figure out the direction of magnetic force that is gonna pull charges inside this top bar. Well, V is that way. Magnetic field is like this, right? Here's the magnetic field. This is the magnetic field. Which means the magnetic force is going to go into the board. Which means the magnetic force will pull charge from B to C. So there will be a current, a conventional current from B to C. If you do the same exercise here, the conventional current goes from D to A. And if you do the same exercise in this bar, and I will let you do Friday night before you go in party, there will be no current, no force on this part because the charge will be pulled out of the wire. So there is no force on the charge. In other words, you have a current I that circulates that way. Okay. Now, again, you have a turbine somewhere here that is rotating, and that turbine is connected to the shaft that is attached to a loop that is in between strong magnets created in there. And here's the beauty of all of that. So these loops rotate, and as it rotates, oh wait a second, it's better if I show the previous one. I think there is a better picture here. As it rotates, look at that. As it rotates, the current on the top goes in one direction, indicating, I mean, there is an electric motive force as a result of this rotation, as we saw, correct? And this electric motive force is going to be alternating. So if you connect each one of these loops ends, so the loops is not totally closed, you don't have a circulation going like this. If you had a loop closed, the circulation of current would go this way and that way, this way and that way. Every time, look, when the loop is in this configuration, the current goes in the way I'm showing. If you look towards north, it is clockwise. But once this loop goes and stay in this position right here, so that this part is somewhere in here, the current goes in the opposite direction. So the current in reality goes AC. It goes in one direction and goes in another direction. And if you have the loop cut open like this and connected to rings, slip rings that are connected to brushes that can carry current, then you have an electric motive force that is AC. So you have an AC circuit going on. Okay, and that's how AC currents are generated. Okay, I want to show that to you. So let's go to the inductors. I think I plugged it on. Okay. Let's show inductors. So inductors are like, think about solenoids. So let's say you have a solenoid and you have a current that is increasing. Remember your car going through the magnetic field that is being generated by power lines? Okay. So the current is increasing and is going through this wire here, which means the magnetic field inside this solenoid points in which direction? Well, points from here to there, and in fact is indicated here, right? Now, if the current increases, it means the magnetic field itself is increasing. And if the magnetic field is increasing, it means Mother Nature creates an induced field, remember Lenz's law, that attempts to prevent that growth, which means the induced magnetic field is pointing from left to right. And the current responsible for that is a current that has to be the other way. So you have a induce the current that opposes the growth of that one, right? Because the current is increasing. So we have this works as if there was a power supply that is shooting up current in the opposite direction, preventing the current to grow as it should, or as it, I can't use the word wanted. By the same token, if the current is decreasing, the EMF generated is going to go the other way. So you define the so-called self-inductance as a property of the circuit, property of your solenoid, that is proportional to the number of loops it has. So the more loops, the more self-inductance it has, and is proportional also to the magnetic flux in it. Okay. So and then wait a second to the previous page. So that your voltage is proportional to, which we saw by Faraday's law, the voltage generated is proportional to the number of loops, to the and to the variation of magnetic flux. So we are saying, hey, there is something called self-inductance that is a property of the material and the circuitry, that's the way you built your solenoid, that is going to be given by the change of current over time. If the current changes, the magnetic field is changing. Changing magnetic field is due to the change in current. So self-inductance times del E over del T. And then you have this handy-dandy set of equations relating self-inductance to the magnetic flux. Okay. And in a circuit, again, we will do problems in class after spring break. In the circuit, in the RL circuit, like that, the solenoid or the inductor has the property of retarding the growth of current, basically. And this is the if you do your the time constant, by the way, the time constant, remember, for capacitor was RC. The time constant for this type of component, which is the inductor, is the inductance divided by resistance, L over R. And pretty much that's it. I will be available over spring break. If you are working on your problem sets and you want to ask questions, email me. I will be available. I will be around. And have an awesome spring break, all of you.